In this video, we're going to talk about the golden thread pattern. First of all, we'll just briefly cover the resource-oriented computing abstraction, and then we'll use this diagram language to explain how the golden thread pattern works. We'll then go on and show a practical example of the golden thread pattern in action. This diagram shows the broad principles of resource-oriented architecture. It consists of a requester, a software function, which resides in an address space. The requester at some point decides it needs some information. It requires a resource value. It issues a request for that resource into the address space. The address space essentially contains an abstract set of the resources, logically decoupled from the requester. When the request is issued, it's resolved to an endpoint that can fulfill the request. Here, the endpoint does whatever it needs to do, including potentially issuing further requests for more resources. Eventually, it's accumulated the state that it requires in order to return a representation of the resource that was requested to the requester. This broad general picture will be familiar to those of you who understand the web. It really could be used to describe the web architecture, where the address space is the URL DNS resolution mechanism, and the endpoint is a web server, the requester being a web browser. In this picture we're going to paint, we're going to show how this model can be applied internally. So this can be actually a software function, this can be another software function, and the relationship between them is mediated through some address space. Okay, let's look at the golden thread pattern in detail. We showed that a requester issues a request for an abstract member of the set. It's resolved to an endpoint. The endpoint computes a value, the representation, and that's returned to the requester. Because the endpoint and the requester are physically decoupled, and the relationship between them is mediated by the address space, then we're able to understand and track every resource that is required in order for this representation to be computed. Therefore, this representation, if appropriate, can be stored in a cache rather than be recomputed each time it's needed. We can also associate with that computed value in the cache a dependency hierarchy of all the resources that must be valid in order for us to still serve this whenever it's requested from the abstract set. A trick we can pull in the RSC world is to understand that there are physical resources that are dependents of this representation, but it doesn't prevent us from imagining a virtual set of logical virtual dependencies. So when the endpoint computes a value, it can, if it wants, associate with this representation a virtual dependency. This representation will continue to be served from cache as long as all its physical dependencies and all its virtual dependencies remain valid. Therefore, the requester, when it asks for these abstract resources again, will hit the cache repeatedly until some expiration occurs. Looking at the representations in a system, in an RSC system we generate lots and lots of representation values. It's quite common for us to have a set of these resources be associated with some common part of our application space, perhaps associated with a virtual dependency, and some other subset of this resources dependent on some other part of our application through another virtual dependency. If some state change in our system is programmatically required, we can issue a request to cut the golden thread associated with the appropriate subset. So here we cut the golden thread associated with dependency 2. We instantaneously and atomically expire all of those representations which depend on this golden thread dependency. Those that aren't affected continue to be served from cache.